Let's look at the 1130 computing system and the manner in which it can be used with our particular reservoir problem. The program, after having been written, was punched into a deck of IBM cards, along with the data to solve this problem. This program is now being loaded into the computer's memory where instructions are stored by pressing the following buttons on the card reader and these buttons on the 1130 console. The program is now being read into the computer's memory. The cards are being read at the rate of 300 cards per minute. During this presentation, I will talk about basic computer concepts, a little about the history of computers as they affect engineering, and some concepts in man-machine communication. I will also demonstrate IBM's 1130 computing system and talk about engineering applications. As a college professor in 1962 and 63, I was continually being asked by my head of department as to when I would be incorporating the computer in my courses in structures and mechanics. Having learned something about computers in the mid-1950s, I had made a judgment that there was no place for the computer in these courses. However, to reaffirm my stand, during the summer recess of 1963, I went to IBM to learn more about modern computers and programming. The net result was that I became fascinated with the modern computer and its potential on the field of engineering, and so I joined IBM. In the 50s, computers were very expensive and difficult to communicate with. This has changed dramatically in the last decade. A short story about two IBM computers will prove these points. The 701 was a giant computer in the mid-50s. It was a computer that was placed in just about every important laboratory in the United States. It was also the computer that got our aerospace and atomic energy programs going. In February 1965, IBM announced the 1130 computing system. By IBM standards, the 1130 is the smallest computer we have ever marketed. There are some striking similarities between a giant computer of a little more than a decade ago and what might be referred to as a baby computer of today. There are many parameters that can be used for comparing computers. One of these is the computer's memory. By this we mean the amount of information that a computer can retain at any point in time. If one is to look at the memory of the 701 and compare it with the memory of the 1130, one will find that for all practical purposes, both computers have identical memories. A second parameter that should be used for comparing is speed, the speed at which the computer processes information. There are many different speeds that may be talked about. Let's look at one. It took the 701 12 microseconds, 12 millionths of a second, to dip into its memory and get some information that could then be manipulated. It takes the 1130 3.6 microseconds to accomplish the same thing. So, on the basis of this parameter alone, it can be said that the 1130 is at least 3 times faster than the 701. The similarities stop at this point. The 701 was a giant in more ways than one. It weighed 10 tons. It required a tremendous amount of floor space. The 1130, its size is negligible. It is essentially the size of a desk. 2 men can pick it up easily. To operate the vacuum tube 701, we required 80 kVA power. To operate the 1130, the required power is 2.2 kVA. The reason is that the 1130 is truly a third-generation computer, completely transistorized. It represents the ultimate in today's state-of-the-art in electronics. To keep the 701 functioning, required 20 tons of air conditioning, none for the 1130. If the human being can be comfortable in a certain environment, the 1130 will be comfortable. Now, if one were interested in the 701 a little more than a decade ago, IBM was very happy to furnish one for $20,000 per month. We have been taking orders for the 1130 since February of 1965. Our prices begin in the neighborhood of $700 per month. The computer is a calculator, a device which can be used for doing arithmetic. It can add, subtract, multiply, divide, and it can be taught to evaluate square roots, logarithms, trigonometric functions, and even to raise numbers to powers. The computer is more than a calculator, however, in that it possesses a memory. It has the ability to remember information. This information can be looked upon very simply as being either data or instructions. We can look upon the computer's memory as being a long train of digital information. These digits could be viewed as being decimal numbers, and we can have many thousands of them stored in the computer's memory. To the computer, many of these digits represent instructions. The remainder of them would represent data. The instructions vary. There are instructions for doing arithmetic, instructions for adding, subtracting, multiplying, and dividing. There are transfer type of instructions that permit us to move information around within the computer's memory. There are instructions that we refer to as read instructions for bringing information into the computer's memory, and write instructions for getting information out of the computer's memory. The computer also has the ability to make logical decisions. This concept is a very simple one. In a computer's language, there is an instruction that gives it the ability to make comparisons. We can tell a computer, go into your memory and compare the number that exists at this location with a number that exists at this location. In essence, the computer does a subtraction between these two quantities. The circuitry within the computer has the ability to determine, upon making the comparison, whether or not one number is bigger than the other, smaller than the other, or equal to it. On the basis of this very simple concept is based all the logical decision-making capability of the computer. And it is this concept that gives the computer its tremendous power to operate on problems. So essentially, our computer is a calculator with a memory that has the ability to follow instructions. And finally, from an engineering viewpoint, it also has the ability to check all of the operations it performs. We can now take this discussion one step further. We go beyond the computer and talk about a computing system. This can be looked upon as consisting of, first, the computer, which really requires three distinct units. The storage unit, where the computer's main memory exists. The arithmetic and logical unit, where the basic circuitry exists for executing the arithmetic and logical decision-making instructions. And a control unit, where the circuitry exists for analyzing and executing instructions, as well as for performing the overall actions of the computer. In addition, we must have input and output to our system. This input could consist of either a keyboard, a typewriter-like device for getting information into the system, or IBM cards, or paper tape. Output for our system could be either on a console typewriter or on a printer where a complete line of information is outputted from the computer at one time rather than a character at a time as we get on a typewriter, or IBM cards, or on paper tape, or in a pictorial or graphical form by means of a plotter. Now, let's get into a brief discussion of communications between man and machine. Earlier, I had mentioned that one of the conceptions I had with reference to the first computers was the fact that these computers were difficult to communicate with. We are now in a position for the engineer to communicate directly with the computer. The vehicle for doing this is a programming language called Fortran. Fortran stands for Formula Translation. It is a language very much like algebra. Let me illustrate the use of the Fortran language. A very common problem in engineering is the three-reservoir problem, where three reservoirs having different elevations are interconnected with a network of pipes. The solution of this problem can be obtained by making use of Manning's equation. Manning's equation is somewhat messy because of the fact that it has fractional exponents for some of the variables in the equation. We can communicate this particular relationship to the computer in a very convenient fashion. Using the Fortran language, this is the way we would present this equation to the computer. Instead of using the variable Q, we could use the word flow. We could say that flow is equal to a constant, 3.1416, where this represents the quantity called pi. Pi must be multiplied by a diameter. This must be raised to a second power to square it, divided by the quantity 4. Pi d squared over 4 is the area of a circular pipe. The asterisk represents to the computer multiplication. The double asterisk represents to the computer exponentiation, the raising of a number to a power. The slash represents to the computer division. The area of a circle must then be multiplied by a constant, 1.318. This must be multiplied by a quantity C, which stands for the coefficient of roughness of a pipe. This will be multiplied by a hydraulic radius raised to the 0.63 power. You will notice the use of the double asterisk for exponentiation. We must then multiply the slope raised to the power 0.54. By defining certain operators in a specific form, in essence, we end up with a Fortran expression very similar to the basic algebraic equation. As an additional illustration of Fortran, let's consider the problem of getting information into the computer's memory. Using Fortran, all I need do is write the word read, followed by two numbers, followed by the information I would like to put into the computer's memory. This statement really says to the computer, read on one of the input devices, and a 2 would refer to a specific device. The 50 would reference a specification that would be used in conjunction with the information going into the computer's memory. I would be reading on a device, according to some specification, a specific value for a variable called C in this case, and a specific variable called D. the pipe diameter. To get information from the computer's memory, all I need do is to write the word write, followed by a parenthesis in which there are two numbers, followed by information that I would like to get from the computer's memory. In this case, I would be saying, write on a particular output device, referenced by the number 3, according to a specification. This would tell the computer the size or number of digits that I would be permitting this particular variable to have as it comes from the computer's memory. We are saying, write on an output device, according to specifications, the value in your memory for the variable called flow. The complete Fortran program for solving the 3 reservoir problem would consist of about 30 such Fortran statements. These would include getting the data into the computer's memory, the setting up of all the necessary equations for getting the problem solved, the solution of these equations, which involves the setting up of 4 simultaneous equations and their solution, which utilize special iterative techniques, checking the logic to make sure that the desired accuracy is obtained in the solution, and also printing out the desired answers. All of this takes about 30 Fortran statements. The point that should be made, and that should be reiterated, is that one can learn Fortran quickly, as well as to use it, and that with Fortran, the engineer has a very fast, convenient way of communicating with a computer. My second conception then, which was the difficulty in communicating with a machine, at the present time is really a misconception. Let's look at the 1130 computing system and the manner in which it can be used with our particular reservoir problem. The program, after having been written, was punched into a deck of IBM cards, along with the data to solve this problem. This program is now being loaded into the computer's memory where instructions are stored by pressing the following buttons on the card reader and these buttons on the 1130 console. The program is now being read into the computer's memory. The cards are being read at the rate of 300 cards per minute. At this point in time, the program is in the computer's memory, and their data cards are being read and being processed. Our printer is now printing out the results at the rate of 80 lines per minute. It has taken the 1130 less than 2 seconds to solve our problem. The 1130 has solved a set of 4 simultaneous equations 15 times. Solutions of this problem take engineers working with a desk calculator or slide rule about 45 minutes to perform. All the calculations that are required in the 45-minute solution are being accomplished by our 1130 in less than 2 seconds. There are several other comments that must be made about a computer solution for this problem. Certainly, there's a time element involved in preparing the program. A program of this type could be written in about the space of 1 hour. However, once the program has been written, it can be reused as often as necessary with other sets of data. Solutions to particular sets of data, therefore, can be obtained in 2 seconds per set. Also, the writing of the program would not be much more involved if I were to add several other reservoirs to the system. On the other hand, a manual solution would be much more involved. The applications or types of problems that can be solved by the computer are virtually limitless. In essence, any problem that involves a numerical calculation can be programmed for a computer solution. However, This does not mean that all problems should be programmed for the computer. There are some problems which very clearly should be solved by machine. The problems that involve significant amounts of time of calculations, where an engineer would be tied up for long periods of time doing repetitive and tedious calculations. There are other problems where the amount of numerical work is trivial, but where the amount of thinking is significant. These problems, very clearly, should not be solved by the computer. They can be better solved manually. And for those problems that fit in between, only with experience will an engineer be in the best position to ascertain whether a particular problem should be solved by way of a computer or manually. No longer need we think in terms of solving just the routine, repetitive problems, but we can also be thinking in terms of solving problems which must be solved only once. Because of the ease that exists in communications with the machine, the one-time problem can now be looked upon to the computer for solution, very realistically and practically. There are other advantages, however, with computer programming, such as the ability to make changes, both changes in problem definition as well as changes in data. Both of these can be incorporated in computer solutions with tremendous ease. Thinking specifically in terms of applications and various engineering disciplines, in civil engineering, problems are being solved in the surveying area. Virtually all types of geometry problems are being solved by computers. In the highway field, problems dealing with curves and earthworks. In the structures field, both in analysis and design, we find a large variety of computer programs. And, as was illustrated earlier, in the hydraulics field. In electrical engineering, we can think in terms of programs that analyze electronic circuits, problems that deal with electric load flow, as well as problems that concern themselves with short circuit analysis. In the mechanical engineering field, we can think in terms of solving problems that concern themselves with machine design, pipe stress analysis, or problems concerning heat transfer, heat balance, or even gas network analysis. In the chemical engineering field, computer applications concern themselves with flash vaporization or calculations dealing with multi-component distillation towers. These are just a few samples of some of the areas that engineers have found for introducing computers into their work. Specifically, IBM has much to offer the engineer in the way of computer programming. We maintain a library of programs in a wide variety of fields. These programs are available to any of our computer users. Specifically, with reference to the 1130 computing system, IBM is very pleased to announce they're making available to the engineering community the following programs. First of all, programs or sets of programs that have come to be known as SSP, the Scientific Subroutine Package for the 1130. Included here are routines for permitting engineers to perform advanced types of mathematical calculations, problems dealing with Bessel functions, Fourier series, matrices, logarithms, and polynomials. We are also providing a package of programs in the statistics area. A very interesting program is one that we refer to as CSMP, which stands for Continuous Systems Modeling Program. Very simply, this particular program permits an engineer, in a very simplified manner, to solve differential equations. More specifically, it permits the engineer to simulate an analog computer on our digital computer. You hear much these days about PERT and CPM techniques. PCS, Project Control System for the 1130, incorporates the scheduling techniques, including critical path, and permits one very easily to do scheduling of any type project on the 1130 system. COGO has been one of IBM's most popular programs for some time now. It has existed on a number of our computing systems and is available on the 1130. COGO stands for Coordinate Geometry. It has a very simplified form and permits the engineer to solve a variety of common geometry problems. COGO takes the form of what we call a problem-oriented language, where one has to learn very little about the computer and has to be familiar only with the vocabulary that is specific to the problems to be solved. COGO has a vocabulary in the order of something like 50 words and word combinations like area, distance, azimuth, and bearing. For structural engineering, IBM provides stress for the 1130, which means Structural Engineering Systems Solver. It permits a structural engineer to do a structural analysis of an indeterminate structure. Structures having up to 99 joints and 200 members may be analyzed. Both plane as well as three-dimensional structures can be solved with this program. The numerical surface techniques and contour map plotting package is a most interesting one. This program, very simply, permits one to manipulate surfaces. Given a series of random points to describe a surface, this particular package of programs generates a description of the surface both mathematically and on a point-by-point basis, and, if desired, permits us to produce contour maps describing the surface. We also have a program called the Data Presentation System. This permits us to make effective use of the graphical plotter that can be attached to our system. In the machine design area, we have a program called Mechanism Design for Gears and Springs. All these programs give the engineer a better feeling for the support that IBM is placing behind the 1130 computing system. In my opinion, there is no question that the electronic computer has found a place in the practice of engineering, and that it is just a question of time before the computer will be as commonplace to the engineering field as the slide rule has been for years.